On to the next shape, cones. Cones, if you think about it, here's a cone. It's got a radius, it's got a height, and again, we might refer to that height as not necessarily a lowercase h, but a capital H to show that it's three-dimensional. We also have this L, and once upon a time, we did this in pyramids, where if we were, let me just draw a quick little pyramid here, and we always talked about being Mario in Mario 64 and being on the top of the pyramid and sliding down the middle edge there. And that was our slant height. We still have slant height in cones, but really any line that you would draw from the peak down to the bottom is going to be a slant height because they're all the same length. Capital H again. So now, if we broke down into a net, if you will, a cone, it's really just made up of two pieces. We have the circular base down here, and then the cone part. Well, if you never really realized what the cone part looks like flattened out, it looks like this. And if you think about, if I were to kind of connect together these two ends, it's really part of a circle. And what would we call a part of a circle that uses the center of the circle, basically? Well, this is nothing more than just a sector, okay? So the cone can be thought of as a circular base plus a sector, okay? So here's our sector arrow. What are you doing? Silly arrow. There we go. There's our circular base plus our sector. So the surface area of a cone. Well, we got a circular base, we have a sector, and the sector part here, again, will be referred to as our lateral area. Okay, think of it again as the walls of our cone. It is going to be referred to the lateral. The surface area covers everything. So the circular base, well, we know what the area of a circle is. That's just pi r squared. So pi times radius squared. To that we need to add the sector though. And this is the part that's a little confusing for where you're at right now, okay? In terms of you being underclassmen, freshman-y type people. To derive the area formula for this requires quite a bit. It requires some advanced knowledge of mathematics. So I'm going to give you this formula, and it's pi times the radius times the slant height. Okay, so pi times the radius times the slant height, that is the sector part of this, okay, the lateral area. Okay, so again, pi r squared, that's the base, that's the bottom, if you will, and pi rl, well, that's the lateral area part, the walls. And you might ask, what's that little baby doing down there? Well, I'm glad you asked what that little baby's doing down there. Some of you might recognize that little baby as Pearl, the landlady, from the Will Ferrell short, The Landlady. I'm not really going to show you the video because some of it is pretty inappropriate in terms of language, but if you would like to look up and search the landlady, I believe, or the landlord, Will Ferrell Funny or Die type skit, you can look that up. It's very humorous. But the reason why I bring up the landlady is because her name in the video is Pearl. And I have had students in the past, when this video first came out many years ago, when they saw pi rl, they thought the pi was kind of like P, the R, and the L, and it kind of looked like Pearl, if you will. And so I've just kind of stuck with that. Okay, so if I think of, especially if you watch this video, and you're not offended by kind of strong language, especially coming from a 2 to 3 year old here, you will forever remember that the lateral part of a cone is Pearl, pi r l. Next example we will do together is imagine this triangle now. We're going to rotate it around y equals 5, and we're going to calculate the surface area. Now, the line y equals 5. Well, here's the y-axis. 5 would be really the top of my triangle. Now, that's the point 0, 5. That's not the line y equals 5. The line y equals 5 is this horizontal line that goes through the point 0, 5. Oop, oop, oop. Take it back a notch. There we go. There we go. So what we're going to do is we're going to take this triangle now and rotate it. Instead of before, when we rotated it kind of a left to right motion for example 2, this one's going to go more of an up and down motion, okay? Because we're rotating it around a horizontal line instead of a vertical line. So basically what we want to do is we want to copy a reflected image, if you will, of this triangle up here. So this whole piece here, this is 5 units right here, we're going to repeat those 5 units up here. And this point that's over here is really going to end up being right here, because this distance needs to be the same as that distance that it's going to take to travel around. Come on, get that little point. Get that little point. Nah, I didn't want all that. Come on, come on. Okay. So now let's draw some lines in here. Boom. So we're going to go from here up to here, and then back down. So I have a reflected image, and that's what's always going to happen when we're going to rotate these shapes. It's going to make a reflected image across that particular line that we're rotating around. So if you turn your head to the left or to the right, you should see that these are kind of like mirror objects, right? Now, what is this thing really turning into when we're rotating it? Ooh, that's the tricky part. Well, this point up here and this point down here, they're going to rotate around, right? And we're really going to make a circle out of that. But what about these points up here? They're also going to rotate around into a circle, but there's not going to be anything there. So what on earth is this thing turning into? Well, oh, let me do a different color here. This thing's kind of rotating around and rotating around. It looks like it's going to end up being a cylinder, but can you tell what's happening with the cone part that you might see right here? We really have what is a cylinder with a cone hole taken out of it. Okay? Cylinder with a cone hole taken out of it. Now we need to discuss the surface area of this. So this isn't just a cylinder, it's not just a cone. And you might think, all right, well, are we going to take the surface area of a cylinder and then subtract away the surface area of the cone because the cone is the whole part? No, we're not. And that might confuse you a little bit at first. This would be the case if we were calculating volume, which we will get to soon. But here's where you need to really stop and ask yourself, what surfaces of this type of shape can I touch? So let's do this from left to right. Can I touch this circle that's over here on this end? Yes, we can touch this circle. So let's talk about the pi r squared, the area of this circle. Well, what is the radius of this circle? Well, the radius is 5. So we'll say the left end, which is a circle and has a radius of 5, well, that would give us an area of 25 pi. Cool. Now, as we're moving from left to right, we can now have kind of the outside part of the cylinder, right? And it's going to wrap all the way around, and there's going to be no hole or anything in it. And so we have the lateral part, the wall, if you will, of the cylinder, okay? This part. Now, the formula for it was pi times diameter times the height. And the diameter, well, if the radius is 5, the diameter is 10. But what's the height? The height is now on its side. It's this length right here. Well, how far is that? It's 8. And so pi times 10 times 8 makes 80 pi that we can touch going around the outside. All right, let's keep moving down. Can I touch this circle that's right here? Is there an actual circle there? No, it is a circular hole. So I do not count it as part of the surface area. And now you might go, well, we're done then, right? Not quite. There is part of the cone that we can touch, right? If we go inside this hole, we can touch the inside part of this cone. It's there, right? Now, what part of the surface area formula of a cone is that? That's Pearl. We can touch the Pearl part of this cone, which is the lateral area. So the lateral area part of the cone that is inside this shape, we said was pi RL. We know the radius is still 5, but what's the slant height? The slant height would be that piece right there, right? From here to here. Well, man, how on earth are we going to figure that out? This problem just keeps getting more and more ridiculous. Well, if the radius is 5 and the height is 8, and do you see the right triangle that basically we have right here? We've got a right triangle where we know 2 out of the 3 sides, and here's our slant height. We're going to have to use Pythagorean Theorem. Now you're thinking, geez, oh Pete, can this is just getting flat out ridiculous. So 5 squared plus 8 squared equals slant height squared. 25 and 64 together make, what, 89? And we square root that, and we get that the slant height is the square root of 89. Can that simplify? No, it is prime. Oh, getting crazy. So now the lateral area is going to be, well, can't really do much with this. It's 5 times the square root of 89 pi. Now, as I mentioned earlier, the surface area is the sum of all of the surfaces. So now we need to take our 25 pi that represents the circular end on the left. We have our 80 pi that represents the outside of this shape that we can touch, plus the 5 root 89 pi, which represents the inside of this shape that we can touch. Add all those together. Well, all of these numbers are pi numbers, right? So we may add them together, except the 5 root 89 has a square root in it, and the 25 and the 80 don't. So not all of our numbers can truly be added as one cohesive number here. But the 25 and the 80 I can go ahead and add, and that's going to give me 105 pi. And to the 105 pi, I can add the 5 root 89 pi. So you can write your answer like this, units squared. Or if you wanted to, we could factor the pi out of those two numbers and write our answer like this in terms of pi. That it's 105 plus 5 root 89 quantity pi units squared. Wasn't that a fun one? That was so much fun. The last topic, and this will go by pretty short, a sphere can be broken down to be what kind of shapes do you think? And this is kind of a stretch here, okay? Don't get me here that this is a very literal thing, but a baseball, if you will, it's made up of 2 leather pieces, and they kind of cup each other, and we kind of have circles, right? We got a circle here. You can see where this was kind of a circle. There's kind of a circle here. How many circles, if you will, kind of make up the surface of a baseball? Well, there's really 4 circles, okay? And so pi r squared represents 1 circle, and so we're just going to throw our quantity factor of 4. Okay, really 4 circles can make up the surface of a sphere. Okay, so 4 pi r squared, surface area of a sphere. So the last problem I'm going to have you guys tackle, because this one covers all of our 3 shapes that we discussed. We have a partial sphere, a hemisphere, if you will, on one end of this shape. We have a cylinder in the middle, and we have a cone on the end. Now, here's what I want you to keep in mind, again, with terms of surface area. Only the surfaces you can touch. So I'm going to give you a hint. Can you touch the circular part of this cone? No, you cannot. Why can't you touch the circular part of the cone? Because there's a cylinder butted right up against that circular part. So there are other pieces of these individual shapes that you cannot touch and you may not include in the surface area. So we will go over, again, those 2 problems the next day in class. And that is all for video 5.